Okay, awesome. All right, great to be here. Thank you all for attending this seminar. I wear two hats currently. I'm an assistant professor of computer science at UCLA, where I direct a machine intelligence lab, and I'm also a co-founder at a new generative AI company called Inception. And today I'm very excited to present some of my group's research at UCLA on building foundation models for planetary scale science. So, if you think about atmospheric sciences, it's a very exciting time for the field because there is a huge challenge that's facing the entire globe. Last year and this year, there's almost been no part of the globe that's been spared by an extreme weather event. And these events, from being rare, are becoming more and more frequent with every passing day. And with all of these events, there is a natural question in front of us, which is how do we build technology which can better help us forecast these events and mitigate their response, mitigate the challenges that come with these events. On the other hand, I'm a computer scientist by training, and most of my research career has been centered around generative AI. And generative AI has also been at the forefront of a different kind of revolution, which is affecting language, vision, and a lot of decisions in our everyday lives. And this is also something which we are seeing more and more in scientific domains as well. So, thinking about the AlphaFold, which was one of the Nobel Prize winning discoveries, again enabled by fundamental advances in generative AI. So, looking at these two worlds, one of atmospheric sciences, which calls for new technological innovation, and the other where AI is supposed to be helping us answer the hardest questions, whether it's in language or vision or science, there is definitely one question that has inspired a lot of my group's research is how can AI influence the state of atmospheric sciences? So my lab at UCLA works at the intersection of foundation models and atmospheric sciences. So we make core contributions to generative AI and decision making, as well as think about how these intersect with real-world applications in physical sciences and specifically looking at atmospheric sciences as a key focus. And today's talk is going to be looking at specifically atmospheric foundation models. Now, when we talk about atmospheric foundation models, one of the key words that often causes a lot of debate in when we're talking to an interdisciplinary audience is this word model. Like, what exactly is a model? And here we have two different viewpoints depending on which community you talk to. So, in the machine learning community, typically, a machine learning model would be one where you would get access to a data set and train a system to do well at predicting outputs given inputs. And depending on what the inputs and outputs mean, you could have different kinds of tasks like summarization, Q&A, chatbot, and whatnot. Uh, but at the same time, this paradigm of building a machine learning model for every task has also changed a little bit. So even within the field of machine learning, today when we talk about a model, more often than not, we are also thinking about models as being inherently multitask. So we don't take every individual task and try to build a new model for that task. We think, how can we build tasks which are models which are more general in nature? So we might look at the entire internet and learn a foundation model like ChatGPT, which can then be used to answer any kind of text processing task. And this paradigm, of course, language being the prime example that we see around us, but it's also been a paradigm which has been applied to other kinds of domains, for example, for understanding visual recognition and perception, as well as for applications which go in multimodal sense and involve a lot of decision making. Now, um, the word model actually means is also very highly used in the atmospheric science community, but here almost exclusively the conventional notion of a model is reserved for thinking about physical models, right? So systems of differential equations, which would define how matter and energy flow through the atmosphere. That would be a physical model which could help us make forecasts about the weather and the climate system. And of course, these physical models have been a cornerstone of modern technology. Even Nobel Prize just a few years ago was awarded to scientists for building the seeds of this technology. And this technology has also been improving. So starting from the 80s, if we look at where we are in terms of our forecasting skill, we find that not only have we reduced the gap in our forecasting skill across the globe, it's also that on an absolute level, the skill has been steadily rising. So today we can very accurately make predictions for many variables within 3 to 5 days, thanks to physical modeling and all the advances we have made here. At the same time, with extreme weather events on the rise, and that requiring the interplay of so many variables, it's also a question we can ask is, can we accelerate this innovation that we have seen with physical modeling using AI and actually improve this technology for longer lead times as well as for a broader set of variables under consideration? So that's the hope with maybe foundation models. And to understand why foundation models might be helpful, we should also think about what limits physical modeling. So broadly, I think of three kinds of limitations with physical models. One is physical knowledge is incomplete. So a lot of subgrid processes require very complex physics, which is hard to characterize, and that is a limitation which helps, which slows down how well these physical models evolve over years. The second is to run these physical models, you need supercomputer scale compute. And this means that today the physical models are a luxury of a few select labs, usually national labs in different countries, which have these resources to actually run these models at scale. Um, and third is, even though weather and climate are so fundamental to our everyday lives, so everything from agriculture to energy depends on weather and climate, there's very limited ways in which you can take a physical model and then actually repurpose it to directly help us predict aspects of lives which indirectly or directly depend on weather. So things like crop yields, things like energy demand, things like insurance prices. All of these are not directly able to exploit the physics that goes into building some of these conventional models. On the other hand, this is also a place where foundation models can come in and directly address some of these limitations. So if you look at a foundation model is data driven and its performance scales very well with increasing amounts of data and compute. So this is different from a physical model where the performance scales mostly only as a function of compute, but there is no or very limited role that data plays in a physical model. The second is foundation model training is expensive. So you require huge GPU clusters to train these models, but that's still very small compared to the amount of compute that goes into a supercomputer. And this is becoming more and more possible for many, many groups around the world, including in universities and academia, to be able to train foundation models. And while training is expensive, once these models are trained, doing inference or predictions with these models is extremely cheap. So, in that sense, foundation model really democratizes access to this technology across a wide variety of groups, which indirectly then also leads to faster and faster progress in this space. The last bit is um, foundation models. Their motivation has been always to do multitask learning. So we don't build foundation models for just solving one narrowly defined task. We have a set of tooling and machinery developed which allows us to adapt these models to a broad set of problems. And that also means that atmospheric science now could be at the center of actually directly helping with solving a lot of sustainability challenges that go beyond just vanilla weather forecasting or climate projections. So with foundation models, we have a huge opportunity to overcome the limitations of traditional physical models and achieve a level of generality and accuracy that hasn't been seen before. So now how do we build these kinds of models? So that's what today's talk is mostly going to focus on. And the talk would be split across three aspects of a foundation model. The first aspect is data. How do we collect lots of data to train such a model? The second aspect is going to be about what is going to be the training objective to achieve a high level of generality in such a model. And finally, there is going to be this question of we might have trained this model with a certain objective, but like I said, if you want to use it across a wide variety of downstream tasks, how do we adapt these models to help with other tasks that are adjacent to the core forecasting or based tasks that are typically used for weather and climate? So we'll look at algorithmic primitives derived from machine learning, which help us think about these three different aspects of any foundation model. And just to ground this in terms of what kind of generality we would be interested in, so we would be thinking about how can we derive a single model which can do forecasting at different time scales, a single model which can then be used for spatial downscaling, a single model that can then be used for different kinds of climate and sustainability related predictions. So whether it's in assessing climate projections many decades into the future, whether it's in helping in other fields of sustainability such as crop yield prediction, many of these we will think about being solved through a single atmospheric foundation model. So let's jump right in and we'll go over these three parts. And for the purpose of exposition, let's first start with thinking about the centerpiece. How are we even going to train such a foundation model? What is the core objective that will define this model? So, um, to understand this objective, it's helpful to look at how weather forecasting happens today. So today, depending on what lead time you care about, you have different class of techniques which should do well. So if you're trying to predict in the order of minutes to hours, the best thing you can do is just predict what the state of the weather is right now, and that's a very hard baseline to beat. Persistence is the best thing to do in this regime of lead times. If you go to very higher lead times, then you again would rely on the simplest statistical technique, which is just to look at historical averages using climatology, and that's going to be the hardest baseline. In between is where things get interesting, and you can have predictability that is non-trivial, and that's what typically is where numerical weather prediction shines. So one of the goals with our foundation model that we would try to build using data is to then think about extending this kind of frontier using an AI-based system. And one way to do that is to then think about how can we build a weather forecasting model which works across different time scales. So this is where also there is two different worlds of weather forecasting based on prior literature. And one prior work thinks about direct forecasting. So if I care about making predictions from xt to xt plus h, I directly learn a function that maps the current state of any atmospheric variable to its future state at t plus h. Now, this is a task-specific objective. It's also very fast, doing a forward pass through a neural network, which is how typically you would specify this kind of function, is extremely fast on modern hardware. But then there's also some downsides here. One of the obvious downsides here is we we might be h could be really big. So for instance, here h could be in the order of days or weeks, but we often have sensory data which helps us actually capture intermediate states of the atmosphere as well, which we are not utilizing when we are training this direct forecasting model, one model for every single age. So, on the other hand, there is a second world of weather forecasting, which is more iterative in nature. That's the one in red here. And in iterative, we choose a single time step ahead, which is a delta time scale. And the goal is then to predict t plus delta time ahead. So in this case, what we are doing is we are not predicting directly h at time h ahead. We break this down into delta to delta, so on and forth, and then learn a function which can predict only a small time step ahead. But this function then can be called again and again as a subroutine to predict for from t plus delta, we can again call this function and then predict at t plus 2 delta, so on and forth. So you're training a single model and you can simulate it at different number of times to get predictions. So this is more like a physical model, how a physical model works. But from an AI perspective, it's also good because it uses all the intermediate supervision. So if your delta is small, so typically you would have it as 6 to 12 hours, you can actually use a lot of the intermediate states of the atmosphere to then help predict even at future time steps ahead. Although what happens in practice with an AI system is you, while you use intermediate supervision, you often run into this problem that AI systems are never perfect. So learning the function that maps you from xt to xt plus delta often would be subject to some kind of error. And that error can compound over different time steps, which leads to the fact that for very, very long time scales, iterative methods end up having generally very, very high errors. And these machine learning based systems are not that stable beyond a certain time range. The other question is, of course, we now have to decide what delta is. And if we choose a very small delta, we'll have very high compounding errors. If we choose a very large delta, then this effectively reduces to a direct forecasting system, which has its own downsides. So one of the things that in my group we have been doing is trying to develop a new regime of forecasting, which we refer to as RJI forecasting, which stands for randomized joint iterative forecasting. So the idea here is to combine some of the good things of both iterative and direct forecasting through two key steps. One is randomization. The second is to prove joint predictions. So what randomization does here is instead of predicting at a fixed delta time step ahead, you treat delta as a random variable that you can sample, right? So I could sample different values of delta. So here I'm showing delta 1, delta 2, delta 3. And depending on what I sample, I would be predicting different amounts of time ahead. So typically in an experiment, we would keep delta to be either 6, 12, or 24. So if we sample it to be 12, we're predicting 12 hours ahead, but we could also have sampled it to be smaller or larger. based on a uniformly random strategy. So that's the randomization bit. The second bit that's important here is the joint iterative. So to prevent compounding errors, we need to also tell the model how it's going to be used at test time. During training, if we just tell the model to predict t plus delta ahead, whereas at test time, if we keep running this to predict at a very long lead time, the model doesn't know that its forecasts at delta ahead will actually be used as inputs to repeat this process. And this can be avoided by actually making the model predict many, many time steps ahead. So given an xt, we predict at t plus delta, t plus 2 delta, so on and forth until t plus k delta, where k would typically be a few time steps ahead, 6 to 8 time steps ahead. So in this way, the model has some knowledge even during training that even though at test time we will go in these steps, we should be able to learn the features which help us predict multiple time steps ahead, not just at delta. So with these two things, we essentially get this new form of forecasting that borrows the best things from direct and iterative approaches. And really, it starts showing multitask learning because now we are treating delta as an input to the network essentially. And this input then helps us decide what is actually the output variables being predicted, similar to any foundation model where the input decides what exactly is the task being done. And the fact that we are predicting many outputs, not just t plus delta, helps us then reduce the train test mismatch because the model learns to have lesser compounding errors in practice through this. So once we combine these approaches, first we'll just look at ablations and then we look at the combined effect. So here on the left, you're looking at the effect of randomization. So randomization, if we had used a fixed delta, which is what prior art would do, you would find that the errors would increase as the lead time increases. Whereas in our approach, which we call as Stormer, we use a randomization of across these different deltas, and that often leads to a lower root mean square error as a function of time. So here, the errors keep increasing for a fixed delta, but they're somewhat reduced. They're somewhat more controlled if we randomize this delta. The second, um, the second part of this approach, which is joint forecasting. So recall that we are predicting k different variables. So if you look at a baseline which only predicts t plus delta ahead, that's k equals 1. And there, if you look at the root mean square error, again, that increases much more sharply as a function of time, as opposed to if we taught the model to predict not just t plus delta ahead, but a few different k times delta ahead. So both of these together also are improving the ability to forecast at different time steps. And here is their combined effect. So when we released this work, the state-of-the-art AI-based approach was based on GraphCast from the team at Google, and another popular approach is Pangu Weather from one of the teams in Hawaii. And both of these are AI-based approaches. And here I'm showing you three different variables: temperature, wind, and relative humidity. And for each of them, we are looking at the root mean squared error as a function of lead time on the x-axis. And you can see that if we look at some of the baselines just to set ourselves in perspective, persistence, of course, if beyond just a few minutes, it starts being a little bit worse than other methods and it keeps becoming worse. Climatology gives you a fixed error which starts becoming very competitive after 2 weeks. All the other approaches start with low errors and keep increasing, but the Stormer-based approach actually reduces at a very controlled rate and in fact is able to outperform climatology all the way up till 2 weeks. whereas the other approaches stop being having any non-trivial skill beyond, let's say, 8 to 10 days. So Snormer was the first approach which was able to show that AI models can have stable predictions and they can hold these predictions up till 2 weeks and outperform climatology until that regime. So this was taught us the fact that even weather forecasting, doing it in a multitask sense, actually can lead to learning very rich representations. And in later parts of this talk, I will show how can you better use this as a pre-training objective and combine it with data and fine-tuning methods to build the overall foundation model. Um, so I'm happy to take questions now or do it at the end of the talk. So if at any point anyone has questions, please feel free to pause me and bring forth any questions.
Okay,
Okay.
Aditya, there is one question from the online audience from Moti Gupta. In RGI forecasting, when you predict x t plus d, x t plus 2d, x t plus 3d, etc., do you do autoregressive rollout or different heads per lead time? And how do the multi-time step loss, how it is computed?
Yeah, so it's a great question, and we do multiple heads. So we take the average loss. It's a weighted average, so we still weight t plus delta more than t plus 2 delta, t plus 3 delta, because eventually you want to predict at test time only delta ahead. So that's the most important prediction to get right. But the other components are something which prevent compounding errors.
Any questions from the physical audience here? Yes.
Hello, sir. Can you please again repeat about the joint iterative part of the RGI forecasting? What does the joint iterative mean?
So it basically the joint word comes from the fact that we are learning a joint distribution. So normal iterative forecasting learns the probability of xt plus delta given xt, whereas what we are learning is a joint probability of xt plus delta, and so on and forth until k delta ahead given xt. So what this looks like maybe in a neural network based approach is you feed in xt and you feed in delta, and then you jointly predict what the state of the atmosphere would be at different delta time steps ahead. So delta, 2 delta, all the way until k delta.
Okay. Any other questions? You have yeah, okay.
Hi, Aditya. This is a very nice approach, but still I want some clarification how the compounding error is reducing in case of your RJ method. So you are still doing T plus delta, T plus 2 delta, and delta is, I think delta is fixed, but we are just doing T plus delta, T plus K delta and all. So every time the error is still there and it is compounding. So how it is going reducing in terms of the normal iterative method?
Yeah, so the error doesn't vanish, but the features that we learn given an XT are looking at also the fact that you have to also predict not just let's say 6 hours ahead, but you also have to learn features which would be more at higher time scales like synoptic scale time scales, because you're also predicting 2 delta, 3 delta. So there is no bias that you are only good at predicting very short term, which would require a certain set of features which are good at for let's say 6 hour predictions. But you think about what features given XT would then also be helpful in predicting future weather. So in a sense, it's trying to make sure that there is a lot more teacher forcing that happens during training from the data itself to tell you how all of these predictions can be physically plausible. So that's what you're optimizing during training, and that's what empirically shows up as uh, one which reduces these compounding errors compared to, let's say, an approach which was only doing iterative. So any of these, like the blue curve here, is not doing joint forecasting, and that ends up having a slightly higher compounding error compared to if you were predicting many steps ahead.
And another small question, you are putting delta as an input, but generally delta is fixed. So in the input, how and why we are giving delta as an input?
Yeah, so that's the randomization part. And again, the idea here is you don't want the model to be biased by the choice of delta. And this is the empirical study showing that if you fix a certain delta, some of these deltas, like for example, delta 12, which is the orange curve, is better than the green curve, which is delta 24. But when you start going towards higher prediction, they can get flipped, right? So there is a trade-off depending on what value of delta you take.
Yeah. Oh, you mean you are giving different delta as an input and during the training time, no?
Yes.
So delta is just like a vector, not like it's a simple one value. No?
No, it is a scalar. It's just randomized. So this is still like one number,
Randomized
but
during every epochs or randomized in the initial?
yeah, randomized in every forward pass.
Every epoch. Okay, fine. Now it is clear.
Okay, so let's move on to part two, where we start talking about data. So now, data is very important for any foundation model. So, in fact, one of the seminal papers from the last few years, which was on the scaling laws for large language models, show that you can predictably say something about the test flaws as a function of how much data you use for pre-training. And the relationship looks like a power law, as this left graph shows. There has been follow-up work which shows that this picture is a little bit more rosy. What actually happens also is it depends on whether you are seeing distinct data points or whether you are repeating the same data points. Your test loss could decrease in a different scaling law. So on what you're seeing on the right is if you look at the bold curve that shows that if you were repeating the data at every solid point here, your test loss would start deviating from if you had access to unique data. So the summary here is large data sets are really important for foundation models, but those data sets should also be very diverse. Because if they're not diverse, the loss is going to go shrink much slowly compared to if we had access to unique data points and we could train for really long. So how do we think about these results in the context of atmospheric foundation models? So here we have some challenge. So unlike language and vision, atmospheric data sets are generally less diverse. So think about your atmospheric simulations. They would look something like this, which is in a way sort of a movie playing, but this movie playing is actually going to be much less diverse compared to all the kinds of movies you would find on YouTube. And even more so, the geometry of this data is actually very hard to um, feed into normal neural networks. So the geometry is highly multimodal. So unlike videos where we are only looking at red, green, blue channels, typically here you can have many variables and pressure levels in addition to the 3D structure. So given these kinds of limitations, one has to think about new ways of sourcing a more diverse set of data for building atmospheric foundation models, and also new kinds of embedding techniques to deal with the highly multimodal nature of these data sets. So, uh, first, thinking about data diversity. So, data diversity is a big challenge. So, just to give you some sense of rough off the envelope calculations of how the magnitude of data is a severe bottleneck for atmospheric foundation models. So, most of the weather forecasting systems that are trained today using AI use ERA5 data set, which is an hourly reanalysis data set starting from 1979 to the present. So it contains about 45 variables at hourly intervals. So you have essentially 45 times 365 times 24 frames and sorry, 45 is the pressure levels and you have about 225 different variables. So comes to about 90 million frames. In contrast, if you look at videos, YouTube has 13 billion videos, and this is increasing much, much faster. So essentially, we are dealing with a very, very tiny fraction of data compared to what typically somebody would use to train a foundation model in a closely related data type, in this case, videos. The other limitation of ERF5 as a data set is that it only captures the recent past. We do have some reconstructions of paleoclimates which are not captured. We have a lot of projections about the future which do not go into training of these AI systems. So one of the experiments we did in our quest to build a foundation model was to think about how can we combine ERA5 with more data sets, and specifically the ones we looked at were coming from the climate modeling literature. So CMIP6, for instance, contains model simulations from much, much more in the past, starting from 1850, going much more into the future up to 2100. And they model different kinds of physics, and those can be then used to define different kinds of couplings and forcings to simulate a large variety of scenarios of how the atmosphere could evolve in the future. So in a way, this is actually also something which is very common in machine learning, where you have a lot of simulation data and you have some real data. And the question then always is, how can you make sure you can utilize the simulation data, but at the same time, make sure the signal to noise ratio does not go too low. So that was the challenge here. And one of the experiments that we showed that indeed these two can be synergistic is what we have here. So what are we seeing here? So we are seeing four different variables, so geopotential, temperature, and wind. And what we're seeing is, again, the root mean squared errors. So this is for 3-day forecasts. And on the x-axis, now we are seeing the size of the data. Now, how are we measuring size of the data? Well, we're measuring the size of the data based on how much simulation data we add. So here at different points, we keep adding more and more data sets from CMIP. And every time we add a new data set, we train on it and we monitor what the loss is on the test set. So what we're seeing here is the loss is going down as we add more and more data, and that's true for across the variables. So more simulation data is reducing the test loss on real data. So that's point number one. And in fact, this reduction is more as and when we start increasing the model's hidden dimension. So here we're using transformers. So D here is the hidden dimension of the transformer network. And we start seeing that if you had bigger and bigger transformers, you'll actually start seeing more significant effects of these adding more data sets. So the point to note here, which is x-axis is showing just the simulation data. Y-axis is showing the effect on real data. So there's a very positive sim to real transfer here, which bodes really well for the future of building atmospheric foundation models, because there is just so much simulation data that we could be using to better pre-train these models. And this is just one of the first evidence of that at scale. So the second aspect is about the dimensionality of atmospheric data. That's typically very large, and that often means that we would need new ways to embed such a multimodal system. So again, for videos, you would just think of four dimensions like the three color channels and time. Whereas for atmospheric data, you would think about different time steps, different pressure levels, as well as different variables spread across a bunch of latitudes and longitudes. So it's highly complex data. And in the interest of time, I won't go too much into detail, but basically, one of the observations we have seen consistently across our works is that instead of designing specialized neural architectures, which would try to think about 3D transformers or think about graph neural networks, the best thing you can often do is just treat this data like 2D data. So use your regular vision transformers, but just make sure that you define an appropriate embedding which can compress these variables without losing too much information. So we have defined a weather embedding, which essentially does a combination of cross attention as well as some variable-wise patching to make sure that overall we preserve the individuality of each of the modalities. So we don't just collapse each of the variables into a single embedding, but we do so in a way such that that information gets distributed across the network. So the first two layers would preserve individual channels. So there would be some complexity in having a wide number of patches. But then very soon after one or two layers, you would try to do a cross attention to bring this dimensionality down so that the further processing through the neural network is quite scalable. And this is just again showing how important this weather embedding is. So if you use a traditional vision transformer or VIT, that's what people would use for computer vision. And you would find that the root mean squared error is much higher, and in contrast with using a weather embedding, which introduces lesser error on the test set. So this was something about data, like how can we actually inherit value from synthetic data sets, utilize the geometry of the weather models of weather data and design a special kind of embedding to process it. And that's how we solve challenges relating to data engineering for atmospheric foundation models. The last bit is how do we adapt these models? So for machine learning, the goal has always been to make sure things generalize. But generalization has also evolved significantly over the past few years in our field. Traditionally, we would think of generalization being of the flavor that the train and test set do not match, right? So we are still doing the same task. Let's say we are trying to predict 1 week ahead. Um, and it's just that maybe for a certain number of years in the past, we use as training, and then certain number of years in the future, we could think of them as being the real world test set. But in modern machine learning, we have moved moved this target and made it more ambitious. So now we think about not just train and test set being different. Often we think about train and test tasks being different. So as long as there is some semantic similarity in the input and output variables, you could have a model that's trained for medium range weather forecasting and simulate it multiple times in an iterative fashion to try to do seasonal forecasting. And that's something I've been talking about in the previous parts of the talk. But what would be really amazing, something which humans are really good at doing, is to not even think about the input and output being the same modalities. So when we know that it's going to rain tomorrow, we can say certain things about different aspects of our lives. Like we can say something about how much the traffic would be on the roads. A farmer can say something about its effect on crop yields. So the information that we see in the form of modalities should generalize across to other modalities. And this is something which we also would love with an atmospheric foundation model. And this introduces some technical challenges. right? So because we have to think about how can we take a network that's pre-trained on one kind of variables, let's say weather variables, and trying to fine-tune it on different kind of variables. For example, if you're doing climate emulations, we might have greenhouse gas emissions as different kinds of inputs, and we might want to predict outputs which are more of the nature of aggregate statistics as opposed to point-wise estimates of the state of the atmosphere. So both inputs and outputs could change, and we might be thinking about how does a weather forecasting system like the ones I presented before, Clima-X or Stormer, can then be used to do climate emulations. So for these kinds of challenges, one of the things that my group has explored is cross-modal fine-tuning of transformers. So if you look at a transformer, this is how roughly the different components look like for a transformer. So if you haven't seen this before, it's just a bunch of different blocks which have been pieced together in a way that allows for efficient processing of different kinds of input data. And the key thing here to note is out of all these different blocks that constitute a transformer, there are two of these blocks, which are the attention and feed-forward layers, which are 99.9% of the parameters in a transformer. So everything else is actually very easy to fine-tune. These two are the ones which are which take the most number of parameters, and they would be the ones which would take the most time to adapt from one modality to another. So we came up with this scheme, which this was done in the context of general machine learning, and we call this thing a frozen pre-trained transformer. This was the very first evidence of showing that you can take a transformer that's learned on, let's say, natural language, and then you can fine-tune it to say interesting predictions about any other modality. That modality could be an image, that modality could be protein structure, that modality could be solving mathematical problems. All you had to do was freeze your attention and MLP layers and fine tune the rest. So this is what we also did in the case of weather and climate. So we took a model that was trained for weather forecasting and then fine tuned only the blocks which were the ones which were outside of the attention and MLP blocks. And that's what we call as this climax frozen baseline. And what you would see here is not only does this help generalize better than traditional machine learning methods, which used to be the state of the art in this field, like random forest and Gaussian processes, this also does better than full fine-tuning of the original architecture. So that's the baseline here in yellow, whereas the frozen one in light blue gets the lowest RMSE across a wide variety of output variables. So, what notably, when the model was pre-trained, it had not seen either of these input or either of these output variables, but the model was able to efficiently generalize across modalities. And if in this paper on Clima-X, we actually have lots of other tasks in the that we showed the scheme works. So we have shown that how we can use a model that was trained to do weather forecasting and adapt it at test time to do downscaling. How can we adapt it to do regional forecasting? So the model was trained to do global predictions, but then we can zoom in on a fine resolution region inside the globe, and that is also possible. So this is the level of generality. Now, since we released this paper, the community has also shown many applications of this approach. So this model has been used for predicting uh, the crop yields or and how they affect wildfires in different regions of the world. And then it has been used for also doing a lot of tasks which involve predicting damage assessments based on natural disasters and weather variables indicating an impending disaster. We have also used this in some of our own collaborations for predicting land use patterns in the Amazon rainforest. And with Argonne, we are also Argonne National Laboratory. We've also been looking at how these can be used in the subseasonal to seasonal time scale, which is very important when we have to predict extreme weather patterns. So that's the last bit of what the promise is of these planetary scale atmospheric foundation models, to go beyond simply weather and climate, but think about the effect of weather and climate on society and sustainability at large. So finally, the viewpoint that my group takes towards all of this is very engineering driven. We really believe that engineering AI systems is a science, and often when I get this question, what science we discover from these efforts, well, I would say once we can engineer these systems at scale, they would enable a lot of science that was previously unknown. We have seen this with the likes of AlphaFold, and the time is all right to think about these kinds of implications, even with atmospheric foundation models. To make this research just more democratized and expansive, my group has also developed a PyTorch library, which contains a lot of the data sets and benchmarks, tasks, models, baseline models, and evaluation metrics to cover this wide spectrum of engineering infrastructure needed to advance this field further. And with that, I'd conclude and thank all my students who did all this amazing work, as well as a bunch of sponsors for supporting this research. Thank you.
So thanks a lot, Aditya. Thanks a lot for telling about this really state-of-the-art work in of Climax, where you also introduced us to the details of foundation models. So I think that's very important and crucial in the context of this workshop. So thanks a lot for the talk. So we'll take questions. First, again, an online question. What would be your opinion of physics in these models? Earth system models are hard tuned for forecasting but do not work for other downstream. Is there a middle ground? And I think including physics would hurt this transferability of Climax to other input modalities. What would be your opinion on it?
Yeah, so I'm a strong believer in the bitter lesson, which and how that connects to this question is, I think we should really think about how do we enforce or benefit from existing physics in developing these models. And a lot of efforts in the community have gone towards designing physics informed neural networks. So they are often touching on the architecture, or they're touching on the loss function and making it a little bit more consistent with physics. I personally believe that the best way to use physics in developing these models is actually in the data. So the fact that we use a lot of physical modeling data from CMIP for pre-training these models, the fact that reanalysis itself uses a lot of physics in giving us data sets like ERF5, that's the best way to insert physics into these models without really then changing anything downstream in terms of architecture and laws, which I think the more you constrain, the more we are hurting ourselves in terms of generality we can achieve with these kinds of models.
Okay. Now, any questions from the physical audience? Yes, lots of hands are raised. So.
Hello, sir. I am Dipan Chakraborty from IIT Kharagpur. So I have two questions. My first question is, you have shown that due to the constraint of data, you have pre-trained the Clima X model using CMIP6 data, and then you forecasted using ERA5 data. Does that mean that you have fine-tuned the model with ERA5 data? And if yes, then have you faced any kind of catastrophic forgetting?
Yeah, great question. So yes, so we pre-train on CMAP6, we fine-tune on a certain years of ERF5, and then we test it on some held out years in the future, which are on ERF5. Yes, forgetting can happen, although in this case, the curriculum is designed such that the last data you set you see during fine-tuning is the most similar in distribution to the data set for which you want to test. So it's similar also what we see with a lot of LLMs, where if you have a certain use case or application in mind, you want to expose that during mid-training or post-training, and that might come at the expense of losing some of the pre-training information, but that is not that is okay because your test data is usually similar to what you expose the model during post-training.
Thank you, sir. And my second question is, does the ClimaX model is able to learn the multi-decadal or decadal oscillations for the climate?
Not yet. Or, I mean, actually, the right answer is we have not done that yet, but I think that's the next phase. So far, my group has been focusing a lot up to sub-seasonal to seasonal timescales. We have not really looked at decadal, but I think that will be the next phase of research evolving into those timescales.
Thank you, sir.
Okay, next question.
Hello, Aditya. This was a very nice talk. Thanks for it. I have a couple of queries. Firstly, regarding your weather embedding that you have already mentioned about. Is it a dynamic or static embedding that you're talking about? If it is dynamic, so how frequently you do that? And what is the right frequency? Have you explored any such things?
Yeah, so this is a data dependent embedding. So if you change so it's learned on a fixed set of data. So it has some trainable parameters which depend on what data was shown during training. So in that sense, it's it's you can say it's static from that sense, but it takes as input the data point. So it's not the same embedding you would have for different states of the atmosphere. If the state of the atmosphere changes, the embedding will also change. So the function is fixed, but the input to the function could change.
So you could also do this weather embedding in your RGI paradigm that you introduced. So did you try in that paradigm, or this is
Yes, yes. So what I described here is the architecture. Yeah, but how you train this architecture is using RGI objective. So the embedding goes as part of the architecture, and it's learned end to end using the RGI laws.
okay? Thank you. So one last question is: when you talked about the transfer learning, was it also federated, or what kind of transfer learning was this?
This was not federated. I mean, this was you have a task in mind, and then you would fine-tune the model on that task. We didn't have to think about federated learning here.
Okay, okay, thank you.
Okay, next. Yeah.
Hi, sir. Thank you for the talk. I just wanted a bit more clarity on your use of ERA 5 and CMIP 6 data. So my question was that, let's say your model learns some sort of relationship in your current climate scenario, which is in your ERA 5 data, and that relationship may not remain the same when you're using your future projections, right? And you are using that CMIP 6 data. So in some sense, I guess I'm asking is that even if you have the same variable, its distribution may change in the ERA 5 and your CMIP 6 data. So like, how does that work? I mean,
Yeah, that's a great question. And actually, that was the biggest question mark before we did this experiment, which is you are introducing some noise when you have a lot of simulation data through SIMIP. And this is not the exact same generative process that you would have for ERA5. Um, but then this question of like how much these relationships can be different versus them actually becoming diversity is a little bit like, is the glass half full or half empty? And at the end of the day, it becomes an empirical question. So, um, the way we use this data, so one of the key things is like the curriculum aspect, right? So you could have mixed ERF5 and CMIP data into one. We don't do that. We first pre-train with CMIP data, so the model only looks at CMIP data, and then we expose it only ERF5 data. So there is something about even the learning dynamics which makes sure that at the end, we care about doing, if we care about doing forecasts, which we did in this case, the more relevant data, which is more grounded in reality for weather forecast, is ERFI. So that is also an important bit where we make sure that the CMIP gives you a nice base, which where you learn a lot of the physics, and not all of that will be accurate or consistent with ERF5, but then eventually you will show the model ERF5, which is what is most relevant to making forecast for weather.
Just to continue on that line, so I had this question. So, like in the CMIP 6 is a family with a large number of models, right? So, like, did you focus on only some models or different models? And if it is different models, then I mean, CMIP 6 models have like exhibit different kinds of biases. In fact, different models can have different kinds of biases. So, when you are pre-training with CMIP 6, I mean, did that create, I mean, the contradictory natures or the contradictory biases in the different models, did that create any issues related to learning?
Yeah. So I think we did not look at all of CMIP. So we looked at these 5 subsets of CMIP, the one you see on the right, MPI, TI, and the 3 others here. And why we took these 5 was mostly because they had a good overlap in variables that ARF5 had. So it was easy in the sense of doing data fusion using CMIP. But I think that's also where there is an opportunity. Like this was the first work showing that you can actually combine such massive data sets which are simulation based, and this is huge data to train the model on. But now I think we, as a field in machine learning, we're getting more and more ambitious. And this, if you show this to someone who's training an LLM, they'll find this very tiny. So I think there is a big opportunity to explore even more CMIP data sources and look at what's the best way to fuse them in a way that actually improves the SNR. And this is not going to be trivial for precisely the reason you're mentioning, that many of them have different biases. So there will be ideas from curriculum learning and optimization more broadly, which would which might come into play when somebody would think about doing data fusion for an atmospheric foundation model.
The subset of that 5 models which you showed, I mean, was that subset chosen specifically with the aim of reducing biases or something like that, or there were some other considerations?
Yeah. So like I said, it was not for reducing bias. It was just that these variables that the other subsets had some they did not have the big overlap with the ERFI variables. Like here also you can look at, these are not exactly the same variables even amongst these 5. And if you look at even more members of the CMIP collection, some of them have even more distinct set of variables compared to ERF5. So these 5 were just taken based on whichever of these had overlaps with the ERF5 in terms of the variables, but not the biases. We didn't make any assumptions about those.
Okay. Thanks a lot, Aditya. Like it was really good to hear about the like this kind of a state of the art model, and so we will really appreciate your participation in the workshop, and we hope we'll get in touch again sometime in future, maybe. So let's thank the speaker once again.
Thank you everyone for attending the talk, all the questions. Yeah, thanks.